Hello friends, welcome to Mu Lessons. So today we will start with a new topic, that is the electrochemical cells and about electrochemical potentials. So this topic have been read by you in the class 11th and 12th standard, but as an engineering course I want to revise from the beginning. This is a part of electrochemistry we have read before. The new terms are oxidation, reduction, reducing agent, oxidizing agent. So I don't think these are new terms for you. These have already been taught in the previous standards. In case of oxidation, this is a loss of electrons. In case of reduction, there is a gain of electrons. And in case of redox reaction, it involves both the transfer of electrons from one species to another. That is, a combination of oxidation and reduction both leads to a reaction known as the redox reaction. Now in this chapter we will deal with two types of agent, like reducing agents and oxidizing agents. Thus reducing agents are those which donates electron. That means this reducing agent helps in reducing some other species and itself gets oxidized, so it donates electrons. Similarly, in case of oxidizing agent, it accepts electrons. That means it oxidizes the other species and itself gets reduced, so it accepts electrons. Now here are some sample equations where you can see how oxidation and reduction, both of them, takes place. Now some typical oxidizing agents and typical reducing agents. You are quite aware of these standard potentials linking to these oxidizing agents. The first reaction is oxygen with the standard hydrogen. So its potential is given as plus 1.229. We will discuss why it is plus and why some are negative. Generally the oxidizing agents have the standard potential as plus or positive, you can say. MnO4 plus 8H plus 5E gives Mn2 plus 4H2O plus 1.51. This is one of the strongest oxidizing agent, MnO4 minus. Now some reducing agents are like zinc, chromium, sodium. They have the electrode potentials as negative. Now you are quite aware of this voltaic cells. What happens in these voltaic cells? The salt bridge. Here you can see this is the salt bridge. It is full of KCl, that is the potassium chloride. This salt bridge allows the charge transfer through solution and prevents mixing, means the direct mixing of this part with this part. It doesn't allow them to mix directly. In fact, there is a flow of charge linkage, and that links the two vessels in this case. And when there is a flow of charge, or you can say flow of electrons, then EMF is produced in the opposite direction. The spontaneous cell reaction for this is given as Fe2 plus Ce4 plus gives Fe3 plus Ce4 minus, and it generates an cell potential. This cell potential depends on the half reaction potential at each electrode. Here you can see this is the electrodes are provided, and this can be calculated by the Nernst equation, which we will study later in this slide. So this type of batteries are known as voltaic cells. Suppose there will be a question, how long it will acts like giving a EMF, or it will act like a battery. So the answer is, till the reaction is complete it will work, and after the reaction becomes complete then the cell goes dead. That means the E cell, there will be no more EMF produced and the E cell will be zero. So they have limited time period according to the solution concentration. Now the standard reduction potentials. For this half reaction potentials, they can be measured with relative to each other, or with reference to reduction half reaction, or with reference to standard hydrogen electrode or normal hydrogen electrode. The more positive the electrode potential, the better is the oxidizing agent. You have seen in the second slide, the positive value of E shows that they are better oxidizing agent, like MnO4 minus, and the more negative is the electrode, the better is the reducing agent. Is reduced in the reduced form, that is the zinc, that is the negative part. Negative EMF shows it is a good reducing agent. Here also you can see in going down from top to bottom, you can see MnO4 minus has E value of 1.695, and similarly zinc has a value of minus 0.6763. So zinc is a better reducing agent and MnO4 minus is a strong oxidizing agent. Now talking about some reduction potentials, what we conclude from the above things or the studies: the more positive the electrode potential, the stronger an oxidizing agent, and the oxidized form, and the weaker is the reducing agent, the reduced form. That means the more is the electrode potential, it will act better at the oxidizing agent. That means it will be very helpful in oxidizing other substances. And the more negative is the reduction potential, the weaker is the oxidizing agent. We are talking with suppose of oxidizing agent only till now. The more negative is the reduction potential, it will act as a weaker oxidizing agent and a stronger reducing agent. So you can compare both of these things according to our requirements. Now some typical oxidizing agent, oxidation and reduction reaction. This you have seen before. Now this is a format of redox reaction in which both oxidation and reduction takes place, and it's a combination of both oxidation and reduction, and hence it is known as a redox reaction. You have read all of these things in your 11th and 12th standard about balancing the ionic equations. There are several rules how to balance them. First we have to balance the electrons, the number of molecules on the left hand side and right hand side. Then according to that we will add number of water molecules with respect to these H plus ions and so on. There are many rules you have read before. So those are all applicable in this part of your study, balancing the equations, making the redox reactions equation. Now let's talk about the voltaic cell. This voltaic cell reaction is one which gives a positive cell voltage. That means you have seen before, till we will get a positive EMF value, that means the cell is working or the battery works. When the cell becomes 0, that is the E equals to 0, then we say the battery is dead or it works no more. So in this case the spontaneous reaction is one in which positive voltage is given. And where from we get this positive voltage? By subtracting the two half reactions from each other. That is, we have left side vessel and the right side vessel. So they both of them undergo reaction, and after subtracting them, that means here you can see E cell is given as E right minus E left, and these are better noted as E cathode minus E anode. The net reaction is given by E cathode minus E anode, and that is equals to the E cell. Now how can you know which one is cathode and which one is anode? We can't say only the left hand side is always anode or right hand side is always cathode. We can't say like that. So how can you know this? So there are some general conventions. The anode is the electrode where oxidation occurs. You need to remember the part of the cell where the oxidation occurs is always the anode. That means the more negative half reaction potential. And the cathode is the electrode where reduction occurs. That means the more positive half reaction potential. And generally the cell is represented as like this, anode. When you know which part is anode and which part is cathode, you need to write the cell reaction or the cell in this form: anode, the solution content, and finally the cathode. These lines of separation shows the separation between all the three parts. This acts as a bridge. Solution acts as a bridge between this anode and cathode, what we call a salt bridge. Now in our galvanic cells, we had a species being oxidized at the anode, a species being reduced at the cathode, and electrons flowing from anode to cathode. The force on the electrons causing them to fall is referred as electromotive force, EMF. The unit which is quantified this voltage is called volt, given as V, and we know volt is equals to joule per coulomb. We can measure this magnitude of EMF causing electron to flow by measuring the voltage. We keep a voltmeter across as a partition between these two electrodes. One is anode and one is cathode. So this voltmeter gives the voltage difference between these two, and hence it works as a battery. Now in case of cell potential, what we need is to predict what the voltage will be between the two cells without having a measurement every possible combination. Now for that, to accomplish this, we need to know what is the inherent potential of the both of the half reaction cells, and the above statement requires that we need a reference so that we can measure the inherent potential of the half cells, and this is done by using a reference that is known as a standard hydrogen electrode or SHE. Consider the following galvanic cell. You can see this is the anode part, this is the zinc part. In this case, oxidation occurs and zinc itself gets reduced. Here is the cathode part. The digital voltmeter shows the potential difference between these two parts, and here we use a standard hydrogen electrode. This standard hydrogen electrode has a EMF. We have noted is this EMF given as 0.0 volts. So when we compare each of them with this, we will get the inherent potential of each of these electrodes, and finally when we subtract both of this, we will get the net voltage across this voltmeter showing. These electrons are spontaneously flowing from this part, that is the Zn to Zn2 plus cell, or you can say it is the anode. In this it has been oxidized to H2 H plus half cell cathode. This is the cathode part. It means the electrons are flowing from anode to cathode. You can see from this diagram. This diagram is explained very well. Now this hydrogen electrode is used in this case, and hence we will know the inherent property of this Zn. We define the half cell potential of the hydrogen as 0 always. In this case also we have defined it as 0. At 1 atmosphere, H plus concentration of 1 molarity, we have 2H plus 2E minus gives H2, and it is given as 0. Now we can measure the voltage of other cells considering that standard hydrogen electrode as 0. In our example, we have used zinc to zinc 2 plus as anode or oxidation. So in this case, we will see how it happens. Zinc converts to Zn2 plus, releasing 2 electrons, and 2H plus combining with 2 electrons gives H2. So we get this, the final equation of the whole cell. The standard EMF of hydrogen electrode is 0 volt as we have considered before, and hence after adding this whole equation we get 0.76 volt. That is the EMF of the cell. In this case, E SHE is equals to 0. So we get that E cell is equals to E of Zn2 plus, which is equals to 0.76 volt, and this is the inherent electrode potential of Zn. So by comparing with the standard hydrogen electrode, we can find the potential of any of these elements. Now standard reduction potential. Standard reduction potential, the half cell potentials that are determined by reference of SHE. These potentials are always defined with respect to reduction. The name suggests standard reduction potential. So this potential is always defined with respect to reduction. So how these things are reduced? That means zinc 2 plus combining with 2 electrons gives zinc. In the previous one we have seen it in the format of oxidation, that Zn gives Zn2 plus 2 electrons, and its EMF was given as plus 0.76. But in this case we are considering it as respect to reduction. So the EMF, in case of EMF there is a change of sign, that is it becomes E equals to minus 0.76. In this case it acts as a reducing agent. Similarly for copper and ferrous we have used like this. If in constructing an electrochemical cell you need to write the reaction as oxidating instead of a reduction, the sign of the cell potential changes. As I have said before, suppose we are writing Zn2 plus gives Zn by combining with two electrons, and its EMF is electrode potential is minus 0.76. And afterwards, if we write it in a different form, suppose first one is a reduction form and this is in oxidizing form, so the electrode potential cell changes, that becomes plus 0.76. Now you need to remember, for numerical part of view, these cell potentials are intensive variables. As such, you do not need to multiply them with any coefficients of balancing equation. Even if you balance these two equations, suppose you are combining this Zn2 plus and with another equation, and you need to add, multiply 2 or 3 in front of this Zn or to this whole equation, but you will never multiply it to this electrode potential, because these are the intensive properties, and you never multiply with the coefficients of the balanced equations. This is very important. Students make mistakes in this part. This is on the numerical point of view. Now how to write these galvanic cells? We have seen two cells in this case. Then zinc acts as an anode in sulfate solution, and CO2 plus is present in sulfate solution. These two electrodes, anode is a Zn, cathode is copper. So this Zn acts, in case of Zn, it releases the Zn ions, and in this case it accepts the copper ions. Okay, so in case of Zn, oxidation takes place, that is the release of electrons, and in case of cathode, it takes electrons acting as a reducing agent. So for a galvanic cell, E cell should be greater than 0. In this example, Zn, conversion of Zn to Zn2 plus is the anode, and Cu to CO2 plus is the cathode. So Cu2 plus combining with two electrons gives copper, and its electrode potential is 0.34, and Zn oxidizing to Zn2 plus 2 electrons gives electrode potential 0.76 volt. Now while writing these equations, we will add up both of these equations, and hence the electrode potential is the summation of all these two voltages, and we get it as 1.10 volt. In this way we can get the galvanic cell's net potential. Now have you marked these things? We have replaced this copper in a different way. We have reversed the potential for the anode. You can see before. So E cell is E net, that means E cell is equal to E cathode minus E anode. Now for shorthand notations, we need to write it like this. I have said it before, this is the anode part, this double pipe shows the salt bridge, and this is the cathode part. The reaction across anode and the reaction across cathode are given it like this, and they are both separated by this salt bridge. In this case, the salt bridge is KCl. So now how to predict the galvanic cells? Given two cell reactions, how can one construct a galvanic cell out of these both cell reactions? We need to compare the reduction potential of the two half cells, then turn the reaction for the weaker reduction smaller, that means weaker reduction means smaller EMF value or negative, and turn it into an oxidation, that is make it positive. This reaction will be anode and the other will be cathode. I will give you one example regarding this. Here's an example describing a galvanic cell based on the following. Ag plus E minus gives Ag, where the EMF value or the electrode potential is 0.8 volt. Next, for ferrous, Fe3 plus to Fe2 plus gives electrode potential is 0.7. Now when you reverse both the reaction, this second reaction, we get the EMF as negative. In the previous case it was positive, and in the next case it became negative. and in this case we will add both of the equations and we will find the net value of this cell. So the net value of cell comes out to be 0.03, which is greater than 0, and hence we can say this cell is a galvanic cell. Now here is an example for you. For the following reaction, identify the two half cells and use these two half cells to construct a galvanic cell. The reaction is given as 3Fe2 plus aqueous solution gives Fe solid plus 2Fe3 plus in aqueous. So the oxidation number changes from plus 2 to plus 3, and as a solid case it remains as 0. So in this case it changes from plus 2 to plus 3, so oxidation takes place. You know it very well. And in this case, if you see from the opposite side, then reduction takes place. Now we know Fe2 plus combines with 2 electrons gives Fe, and the cell potential is given as minus 0.44 volt. And Fe3 plus electron gives Fe2 plus, and the cell potential is given as 0.7 volt. Now continuing with the same equations, we have got like this. Now we will change the cell reaction into this positive part. You have seen it before, as we have said before. Whenever you convert a reduction to oxidation, the sign changes. So in this case we have converted the reduction to oxidation state, so the negative sign becomes positive, and now it becomes easier to calculate this for the whole balance equation. We multiply 2 to the second equation and we get the result as like this. But as I have said before, never multiply this electrode potential with the coefficients that you are balancing here, that is 2. You should not multiply to 0.7 with 2. There is a simple addition of both of these numbers and we get 1.21 as a net cell reaction potential. So these are some examples of net redox reaction or balanced ionic reactions. Now to find all of this, the effect of concentration and potential, how it affects the cell, we'll need to know a specific equation, that is a Nernst equation. This equation is given as E is equals to EMF of the cell minus 2.303 RT by NF log of the reduction concentration to the oxidation concentration. Here E is the reduction at specific concentration, E0 is the standard reduction potential, N is the number of electrons involved, R is the gas constant, absolute temperature is T, Farad is constant F. So you know all these things better in the previous things. Now for the calculation part of view, we are given MnO4 minus plus 8H plus 5 electrons gives a electrode potential of 1.51, and for hydrogen the molecular concentration is given as 1 molarity. For Mn4 plus it is given 0.1, and for Mn2 plus it is given 0.01. Now we'll use the Nernst equation. Standard EMF minus of 0.05916 by 5, net change of electrons is 5, N into F as I said before, log of this reduction part to the oxidation part. So in this case there is only Mn2 plus, for water it is 0, and we take it as like this. So the net reaction comes up to be, solving this equation we get the net potential of the cell is plus 1.63, and this is with reference to the normal hydrogen electrode. You need to note that this is more positive than E degree, that is this one 1.51, and here we get 1.63. So this value is more than 1.51, and hence it has a greater tendency to be reduced compared to the standard conditions. So by knowing all these things, you will be aware how to use them in the cell and how to calculate them for the cell reaction. Here is another part on the calculation of using Nernst equation. So by going through these examples, you will be well acquainted how to use them. There are various ways of using, by concentration or using KSP values. So the more you will practice in numericals, you will be more acquainted with them. Thank you.